We are in the midst of a scientific revolution brought about by technology and the access to space. And just to give you a sense of how far we've come in just less than a generation, when I was a graduate student, we argued about the age of the universe plus or minus 6 billion years. Today, thanks to space observations, we know that the universe is 13.8 billion years old. You note this says 13.7. That's because this picture is a few years old. We've had better measurements. We're now arguing about that decimal place, right? We now know that most of the matter that causes gravity and forms and shapes the universe is dark matter. We have no idea what it is. 74% of the energy density of the universe is in dark energy. It's making the acceleration rate of the universe increase right now, and we don't know what it is. Only 4%, 4 or 5% of the universe is stuff that we know, particles we can measure, the things that make up the Earth. None of this was known. That was known when I was a graduate student. When I was a graduate student, the only planets that we knew about were those that orbited the sun. Thanks to very precise space telescopes, we now have detected over 2,000 planets orbiting stars in our galaxy. And again, this tremendous progress is because of technological advances and access to space. So in particular, it's the fact that we've had telescopes that span the electromagnetic spectrum. Powerful telescopes that can see microwaves, can look all the way back very close to the Big Bang, the very earliest moments of the universe. Visible light, where we see galaxies, stars, and planets, and also X-ray light. X-ray light where we can see the most energetic phenomena in the universe. This is what I'm going to focus on because I'm the principal investigator of an X-ray telescope called NuSTAR. So X-rays are light, just like visible light. And the X-ray band is broken up into regions. And we've had powerful telescopes that have viewed the heavens in the low energy part of this X-ray spectrum. NuSTAR is the first sensitive telescope that can operate in the high energy part of the X-ray spectrum. And as such, it's opened a new view on the universe. So visible light has colors. X-ray light also has colors. And by studying the colors of objects, we get much more physical information about them. This is a beautiful Hubble Space Telescope image of the antenna galaxy, seen in black and white. All right. If we look at the antenna galaxy in red and yellow, we see dusty regions, cold regions. All right. If we add the blue to the antenna galaxy, we see regions where massive stars are forming. So these colors tell us about the different mechanisms, physical regions in this galaxy. So NuSTAR, by analogy to the visible light, is adding blue, indigo, and violet to the X-ray colors with which we can study the universe. So what is it that enables NuSTAR to do this? Well, we've gone from basically a pinhole camera type telescope. You know, you use a pinhole camera if you want to look at something bright like the sun, to a real focusing telescope. And this has been done over many years using technologies developed in my labs at Caltech and with partners around the world. And what we're able to do now is, with these high energy X-rays, study some of the hottest, densest, most energetic regions in the universe. So NuSTAR is a small explorer. It's the smallest astrophysics platform, the cheapest that NASA launches. And so to be cheap, Ollie will tell you later, you have to be small. And so NuSTAR was launched from a small rocket from under the belly of an L-1011 aircraft, which took off. The rocket launched and then actually goes in front of the rocket, gets into orbit, so it goes around the Earth once every 90 minutes. The ability to launch on this small rocket was very important for being able to do this mission cheaply. Now, the problem with this is that X-ray telescopes are intrinsically large, all right? 10 meters, 33 feet, or the length of a school bus is the size of a payload you need to carry an X-ray telescope. So how did that work? Well, 9 days after launch, this is NuSTAR, we deployed a Tinker Toy-like structure. This is another interesting piece of technology that went into this mission. Piece by piece, out of what we in INT called the trash can, okay? And this folded out on orbit. It took 24 minutes. So I don't know if you watched the Mars landings. Their 7 minutes of terror. This was my 24 minutes of terror because we never deployed the thing fully assembled on the ground. But it worked perfectly, and everything locked into place, and we have our X-ray telescope. By the way, this launch was in June of 2012, and ever since, we've been viewing the heavens with the most sensitive high-energy telescope ever, factors of 100 more sensitive, factors of 100 crisper images. So NuSTAR has told us fundamentally new things about the processes that create the chemical elements from the mix of hydrogen and helium that we had shortly after the Big Bang. So this is a theorist's computation of how the universe went from a soup of hydrogen and helium to the rich mix that we have today. What happened is the hydrogen and helium forms filaments. In these filaments, gas and dust condense and form stars. These stars burn their fuel and explode. They create the chemical elements while they burn, and then they explode and spew the chemical elements out into the universe where they can recondense and form new generations of stars, planets, and eventually life. And what you see here is these supernova explosions. Now, this is a theoretical simulation done on with massive amounts of supercomputing time. Is it really what happens? Many of the details of this are just theory. We need the observational telescopes to test those theories. Now, one of the key mechanisms then for creating the elements are these supernovae. Now, supernovae, like a massive star, uses up all its fuel, right? It collapses and then explodes. And in a massive failure of theory, we cannot, on a computer, make a star explode. What you see here is a computer simulation, and the star starts to explode, and then theorists have to put in ad hoc mechanisms, in this case, the turbulence and sort of sloshing around of the star, in order to make it explode. And so one of the fundamental questions has been, how do these stars explode? How do they get the chemical elements out into the universe? And this ad hoc mechanism is one of them, but is it the one that works? There are many other ideas. Here, we need the observations. So previous generations of X-ray telescopes have looked at the remnants of these supernovae hundreds to thousands of years after they explode. And I want you to just take in for a minute the breathtaking beauty of this. This is a real image of a star, the remnants of a star that exploded. Okay, now what astronomers do with these images, they're kind of like crime scene investigators. They take the distribution of the shrapnel and they try to piece together the workings of the bomb that made it explode. But the problem here is these are made in the red and yellow part of the X-ray spectrum, where you're really only seeing the very outer layers of the bomb, the shrapnel that's way out there. What you really want to do is look at what happened at the heart of the explosion, right? So this is what NuSTAR has done for the first time. By looking in high-energy X-rays, we don't see this hot, glowing embers like you see in lower energy X-rays. We see actually radioactivity, all right? Chemical element, when one chemical element changes to another, titanium changes to calcium, we see that, all right? And we can look at that distribution, and that tells us what happened at the core of that explosion. Here is a famous supernova remnant, Cassiopeia A, seen in the red and green parts of the X-ray spectrum. Here is the new star image in radioactivity, fundamentally different physical process. You can see it looks very different, and what it is telling us, it is directly confirming that this sloshing around of the star is what made this star explode. So I'm going to step back again. All right, I started with the big picture. New star has told us about really one of these fundamental processes that's creating the elements. What's next? Well, NASA and ESA are flying giant infrared and optical telescopes, which will look at a huge swath of the sky at the same time. And by analyzing it, huge, massive computational problem, by the way, it will give us direct clues as to what that dark energy is that makes up such a 74% of the energy density of the universe. In addition, we're going to be flying, ESA will fly a telescope that's not even working in the electromagnetic spectrum. It's detecting literally ripples in the fabric of space-time called gravitational waves. All right, that'll be something fundamentally new. NASA is launching a small mission like New Star, not maybe twice the cost. All right, these are all very large billion-dollar missions. A small mission that will look for planets around nearby stars. And then this isn't from space, but Caltech and partnering with Japan and China and Canada are building an enormous ground-based telescope with the capability to search for signatures of life in the atmospheres of the planets that this mission will find. And so I'm going to leave it there and just say I was asked, well, how does this advance technology? And astronomers are always trying to build the next most sensitive detectors. And in my case, my detectors detect X-rays, the same energy X-ray that your doctor uses, all right? And so my detectors are now being considered for use in medical imaging, also for detecting radioactive materials for Homeland Security. But I want to say, to me, I'm a pure scientist. I'm driven by knowledge. And I think the way that this is going to change the course of human events is because we understand better our place in the universe.